I would like first to thank the jury members. Thank you very much, Isabelle, for having accepted to come here during these difficult conditions. And I would also like to thank the deux rapporteurs for having accepted to evaluate the thesis online. And thank you very much, Armel. Good morning, everyone. I will present today my thesis work entitled Sequential Pattern Generalization for Mining Multi-Source Data, directed by Armel Brun. The project is funded by the e-FRAN Metal project. I will first present the general context of our work. Then I will present the GSPM algorithm, a general sequential pattern mining algorithm, which is our main contribution in our work. It is composed of 3 main steps. Then I will discuss the experiments conducted in order to evaluate our algorithm. And finally, I will present the conclusion and the future work. I will make the presentation in English. However, as required by the doctoral school, I should make a small part in French. Therefore, I will start with the general context in French, and then I will switch to English to continue the rest of the presentation. Je vais donc commencer par donner un exemple pour expliquer le contexte du travail. Considérons un exemple d'un menu d'un restaurant, où notre objectif, c'est d'identifier les commandes qui sont fréquemment commandées par les clients du restaurant. Une commande est composée d'une entrée, d'un plat principal et d'un dessert. Voici un exemple d'un menu où on peut composer notre menu à 20 € en choisissant une entrée, un plat principal et un dessert. Il y a des commandes qui sont fréquemment commandées par les clients du restaurant. Un exemple de ces commandes, c'est une commande composée de cheese balls, burgers et tartes. Et il y a d'autres commandes qui ne sont pas fréquemment commandées par les clients du restaurant. Des exemples de ces commandes est une commande composée de soupe, poulet et kunafa, et une autre commande est composée de soupe, poulet et osmalia. Ces 2 commandes qui ne sont pas fréquemment commandées, ce sont 2 commandes différentes. Mais si nous examinons les éléments de ces 2 commandes, nous remarquons que les entrées et les plats principaux sont les mêmes. Par contre, les 2 desserts de ces 2 commandes sont différents. Si nous regardons plus loin sur ces 2 desserts qui sont différents, nous remarquons que ces 2 desserts sont des desserts libanais. Non seulement ces 2 desserts sont libanais, mais ils sont tous les 2 composés de pistache, du fromage blanc et du vermicelle. Nous pouvons donc considérer que ces 2 desserts libanais sont semblables. Par conséquent, nous considérons que ces 2 menus représentent la même commande. Le problème principal, donc, c'est qu'il y a certaines commandes qui ne sont pas fréquemment commandées par les clients du restaurant, mais intuitivement, on sait qu'ils sont semblables. L'objectif étant d'identifier les commandes qui sont fréquemment commandées par les clients du restaurant. Le premier exemple est un exemple déjà montré dans un slide précédent et qui représente une commande fréquemment commandée par les clients. Le deuxième exemple est une commande qui n'existe pas, mais cette commande est une abstraction de 2 commandes qui sont semblables. On peut donc considérer que cette commande est fréquemment commandée. I will now switch to English and continue the rest of the presentation in English language. Our scientific objective is to understand and analyze the user's activities in order to extract important information from these activities. The scientific problem of our work is that there could be variability among the activities of the users. This could be caused by the problem of similarity between the data elements. This thus leads to a loss of important information. Therefore, our scientific challenge is how to compensate the loss of important information that is caused by the data similarity. In order to handle this problem, we propose a new algorithm called GSPM algorithm, which is a general sequential pattern mining algorithm. Our approach can be viewed from three main viewpoints, which represent three different domains in the literature: sequential pattern mining, multi-source data, and generalization, where we start by mining the sequential activities of the users, as our main objective is to analyze the user's activities. And as we encounter problems of data similarities among the elements, we rely on the multi-source data in order to recover the lost activities from this process, and we propose a generalization process which recovers the lost general patterns and detects frequent general patterns in order to solve the problem of similarity. Let's consider an example of a sequential database SD, which represents sequences of educational resources consulted by the students on their virtual learning environment. Considering that the minimum support is 4, an example of a frequent pattern that could be obtained from this sequential database is R9, R23, which occurs 6 times in this sequential database. Usually in a sequential database, we can only detect the frequent patterns. However, if we consider detecting also the infrequent ones, an example of an infrequent pattern that could be obtained is R9, R10, R23, which occurs 3 times in this database. Another example is R23, R3, which occurs only once in this sequential database. One limitation that we could encounter in this sequential pattern mining process is that the number of sequential patterns could be limited. One of the main reasons could be the variability among the users' activities. This could be caused by the problem of the similarity among the patterns, as certain patterns are similar, and these similar patterns could actually represent the same sequential activity. This could thus lead to a loss of sequential patterns where the support of a sequential activity is distributed among the patterns representing it. The first step, thus, in GSPM is to detect the promising patterns. As previously mentioned, we can only obtain frequent patterns from a sequential database. If you consider obtaining the infrequent ones also, we know that we could not obtain all the infrequent patterns from this sequential database because the problem will be of very high complexity. And in addition, the patterns of very low supports are not considered as important patterns because they are either rare patterns or patterns that are made by error. Therefore, we introduce a new concept of patterns called promising patterns as a first contribution in our work, where we consider that a promising pattern is a pattern that is infrequent, however, it is almost frequent. In order to detect these patterns, we set a second minimum support threshold called minimum support promising, and we detect the infrequent patterns whose support values are higher than the minimum support promising threshold. Considering the same example of the sequential database with a minimum support promising fixed to 2, and considering the infrequent patterns obtained from this sequential database, we consider the first 2 patterns, P2 and P3, as promising patterns, as their support values is higher than the minimum support promising. However, the third pattern, as it occurs only once in the database, it is thus considered as an infrequent pattern and it is discarded. The second step in the sequential pattern mining phase of the GSPM algorithm is to detect the similar patterns among the promising patterns. Several pattern similarity measures have been proposed in the literature in order to detect the similarities between different patterns. Some of these measures is measuring the similarity of the patterns according to their frequency, cosine similarity, or the Euclidean distance. However, as we are mainly interested in determining the different items that occur at the same positions in the patterns in order to use it for a further step in the generalization, we propose a new pattern similarity measure, which is the second contribution in our work. It is a percentage similarity between 2 promising patterns. It depends on the number of identical items at the same positions in the patterns. Let's consider the example of these 2 promising patterns. P2 and P3, which have 3 items. These 2 patterns have 2 common items at the same positions. However, it has at one position 2 different items. Therefore, we can consider these 2 patterns as similar. The third step in sequential pattern mining phase is to check if these similar patterns represent the same activity. We consider that for each 2 similar patterns, if the different items at the same positions in the patterns are similar, then we consider that these 2 similar patterns represent the same activity. Considering these 2 similar patterns, P2 and P3, which have different items at position 2, if you are able to prove that R10 and R52 are similar items, then we consider that P2 and P3 represent the same sequential activity. In a sequential database, we can only have the item IDs, sequences consisting of item IDs, where no additional information about the item is provided in this sequential database. However, detecting the similar items only through their item IDs is limiting because the item ID is the unique identifier for each item, and therefore the results will probably be inaccurate. Therefore, the main question now is how to detect similar items. The next phase of the GSPM algorithm is the multi-source data phase. We introduce a new term of data called multi-star data, which represents multi-source data, relational data, and multi-dimensional data. 2 main approaches were proposed in the literature in order to mine these multi-star data. The first approach is called the data integration approach, which integrates all the data together and performs a traditional sequential pattern mining process on these integrated data. However, the limitation of such an approach is that it is of high complexity, especially when the amount of data is huge. The second approach proposed in the literature is an approach which maintains the multi-star structure of the data. Although this approach is of lower complexity than the data integration approach, the algorithms proposed in this approach are algorithms that are dedicated to their specific multi-star structure of data that they have. And as we don't have the multi-star structure that they have, we propose our own dedicated algorithm. In our multi-star structure, we have 3 main data sources. The first data source is the sequential data source, which contains the user's data sequences of items. An example is students' sequence of educational resources. The second data source is the descriptive data source of users, which provides several data attributes describing the users. An example is the description of the students. The third data source is the descriptive data source of items, which provides several data attributes describing the items. Example is description of the educational resources. The first step in the multi-source data phase of the GSPM algorithm is to detect the similar items. We propose a new item similarity measure as a third contribution in our work, which is a percentage similarity between 2 different items. It depends on the number of common attributes between these 2 different items, where items are considered as similar if they have a certain number of common attributes between them. An example of a descriptive data source of items, where the items here represent educational resources. We have in this database the resource IDs, and we have 4 descriptive attributes describing each resource ID. Considering these 2 different items, R10 and R52, which have these lists of descriptive attributes. These two items have three common attributes. Therefore, we could consider that R10 and R52 are similar items. We introduce two kinds of relations among our multi-star structure data, and this contribution has been published in a workshop and a European conference. The first kind of relation is called the contextual relation, and the second kind of relation is called the complementary relation. The descriptive data source of students provides descriptive data to the students. We view these data as contextual data provided from this data source to the students and thus to the sequences of the students. And we thus consider that the descriptive data source of students is the contextual data source, and thus the relation existing between the descriptive data source of students and the sequential data source of students is thus the contextual relation. By mining these two data sources, depending on the contextual relation, we can obtain contextual sequential patterns. An example of this pattern is a pattern that has 11 years old Nancy as frequent multidimensional information, which is associated to a sequential pattern that is R923, for example. The second kind of relation is the complementary relation, where we have descriptive data source of items, which are the academic resources in our example. We consider that this data source provides additional data to the resource IDs in the sequential data. Therefore, we consider these data as complementary data to the items in the sequences, and we consider the descriptive data source of academic resources as the complementary data source, and the relation between the complementary data source and the sequential data source of students is thus called the complementary relation. The next step of multi-source data phase of the GSPM algorithm is to detect the patterns which represent the same sequential activity. And for this step, we rely on the complementary data in order to obtain complementary data to the items of the sequences. And we consider that for each two similar patterns, if their different items at the same positions in the patterns are similar, then these two patterns represent the same sequential activity. As we can see in this example of two similar patterns, P2 and P3, which have different items at, which have R10 and R52 at position 2, and R10 and R52 are proved to be similar items containing this list of common attributes, then we consider that P2 and P3 represent the same activity. The third phase in the GSPM algorithm is the generalization phase, where it generalizes the similar patterns in order to recover the lost activities. We define a new kind of pattern or a new form of pattern called the general pattern as a fifth contribution in our work, and we consider that a general pattern is a pattern that represents the two similar patterns which represent the same activity. And the general pattern is formed by substituting the similar items in these similar patterns representing the same activity. We substitute these items at their same position by their set of common attributes. In order to better understand how a general pattern is formed, we consider this example of the P2 and P3, which are similar patterns. These two similar patterns have similar items R10 and R52 at position 2 of the patterns. Therefore, we consider that P2 and P3 represent the same sequential activity. And in order to form the general pattern P6 from these two patterns, we replace R10 and R52 by their set of common attributes at their position in the pattern. to obtain pattern P6, which is a general pattern that contains item IDs at the positions where the items are identical in the two patterns, and it contains a list of common attributes where the items at the position where the items are similar. A general pattern is a pattern that does initially exist in the sequential database. Therefore, we could not calculate the support of this pattern by a database scan. In order to determine if the general pattern is frequent, we define a new method in order to calculate the support of the general pattern. And this method is as follows. As we consider that a general pattern represents the two similar patterns which represent the same sequential activity, then we consider that the general pattern, its support value is the sum of the support values of the patterns representing it. Considering this example of general pattern P6 formed from P2 and P3, as we consider that the P6, the general pattern, represents these two patterns, then the support of P6 is thus the sum of the supports of these two patterns, which is 6. And as 6 is greater than the minimum support value, then we consider that the general pattern P6 is a frequent general pattern. A frequent general pattern is thus a pattern which contains at each of its positions either an item ID or a set of descriptive attributes, as we can see in the example of the pattern P6, where it contains item IDs and descriptive attributes. This makes it a rich pattern because it contains various kinds of information in the same pattern, which is a main advantage of such a form of pattern. And another advantage of this pattern is that it represents more than one traditional frequent pattern. Therefore, the data coverage of a general pattern is higher than the data coverage of traditional sequential patterns. However, a limitation of such a form of pattern is that it is less specific than a traditional pattern, because a traditional pattern is formed of patterns containing of patterns having only item IDs, where the item ID is the most specific kind of information, while a general pattern is a pattern that contains descriptive attributes at certain positions, making it less specific than a traditional pattern. In conclusion, the GSPM algorithm is formed of three main phases. The sequential pattern mining phase is the first phase of the algorithm, where it takes as an input the sequential database, the minimum support promising threshold, and the minimum support threshold, and it gives as an output two sets: the set of frequent traditional patterns and the set of similar promising patterns. This set of similar promising patterns is then taken as an input to the second phase of the GSPM algorithm, that is the multi-source data phase. And this phase gives as an output the set of patterns representing the same sequential activity. The third phase in the GSPM is the generalization phase, where we recover the lost activities. This phase takes as an input the set of patterns representing the same activity, and it gives as a final output the set of frequent general patterns, where we have as a final output of the GSPM algorithm a set of frequent traditional patterns and a set of frequent general patterns, which allows us to solve the problem of the limited number of frequent traditional patterns obtained by the sequential pattern mining process. The second step now is to discuss the experiments conducted in order to evaluate the GSPM algorithm. In the METAL project, we have actually encountered difficulties in obtaining an educational data set due to the data restrictions and laws, especially for the students who are less than 18 years old, as there are certain restrictions laws in France for the data collection. Therefore, we could not obtain until now the educational data set, and this is why we perform our experiments on another data set, and we have chosen this specific data set because it contains the multi-star structure that we need, that is required in our approach, and that allows us to make the experiments. This data set is the DAHER data set, which is a data set collected from the DAHER company, music company. This data set contains users' consultations of soundtracks, where we have 2,220 users, and we have around 108,600 soundtracks, where each soundtrack is described by 6 descriptive attributes. The data integration approach previously presented in the literature is an approach proposed in the literature which actually integrates all the data together and then performs a traditional sequential pattern mining process on the integrated data. We consider this approach in order to compare it with our GSPM algorithm. And if we consider applying this approach on the DAHER dataset, which is mainly of 2 different sources of data, then the input data would be sequences of item IDs and their descriptive attributes. In this case, there are 6 descriptive attributes. For the traditional sequential pattern mining process, we use the well-known prefix span algorithm that is an algorithm widely used in the literature, and it is proved to be an efficient sequential pattern mining algorithm. The resulting patterns from the application of the data integration approach on the DAHER dataset would thus be patterns containing either item IDs or attributes or both kinds of information in the same pattern. We have conducted 2 main experiments on this data integration approach. The first experiment is conducted on half of the corpus, which contains item ID with 3 descriptive attributes. The execution of the program with this corpus has taken 1.5 hours, and it has generated around 55 million patterns. The second experiment has been performed on the full corpus, which contains item ID with 6 descriptive attributes. Even on a machine with a high storage capacity, the execution of the algorithm has stopped after 72 hours, and it is probably because of the huge number of patterns that will be obtained and the redundant patterns in this approach. Therefore, this proves the inefficiency of the data integration approach if it is applied on a multi-star structure of data. Now we move to the evaluation of the GSPM algorithm. The parameters that we have in the GSPM are minimum support promising threshold, minimum support threshold, minimum support promising threshold, the minimum item similarity percentage, and the minimum pattern similarity percentage, where we evaluate our algorithm in terms of the runtime and the number of frequent general patterns obtained. We recall that our main objective is to obtain frequent general patterns in order to solve the problem of limited number of traditional frequent patterns. Therefore, until now, there are no rules which allows us to detect the ideal number of frequent general patterns to be obtained, but we consider that as the frequent general patterns are obtained as a backup to the traditional frequent ones, then we consider that the number of frequent general patterns should be significant but limited in order not to overrepresent the number of traditional frequent patterns and in a limited runtime. Step is to evaluate the impact of the minimum support promising parameters on the GSPM, where for all the experiments, we set the minimum support value to 40, and thus the number of obtained frequent traditional patterns is fixed, and it is 1,280 patterns. For all the experiments also, we set the minimum pattern similarity percentage to 80%. And in this specific experiment, we set the minimum item similarity percentage to 80%. And we study the impact of decreasing values of minimum support promising on the number of frequent general patterns and the runtime of the GSPM algorithm. We set decreasing values of the minimum support promising, which ranges from 90% relative to the minimum support until 75% relative to the minimum support. As we can notice from the experiments, from the results of the experiments, we notice that when the percentage of the minimum support promising is 85% of minimum support or above, the number of frequent general patterns obtained is less than the number of traditional frequent patterns. However, when the percentage of minimum support promising is lower than 85%, the number of frequent general patterns obtained exceeds the number of traditional frequent patterns. Concerning the runtime of the algorithm, we noticed that also for higher percentages than 85% of minimum support, concerning the minimum support promising, we noticed that the runtime is more limited than the other lower percentages. As our objective is to obtain a significant but limited number of frequent general patterns, then we consider that the most adequate value support promising is 85% of minimum support, because it allows obtaining a number of frequent general patterns which is close to the number of frequent ones, traditional ones, but does not exceed the number in a limited runtime. Now we study the impact of the minimum item similarity parameter on the GSPM algorithm, where for this experiment, we fix the minimum support promising value to 85% of the minimum support. And as the number of promising patterns depend on the minimum support promising parameter, then in this experiment, it is then always fixed, and it is 2,129 patterns. We study the impact of decreasing percentages of minimum item similarity from 80% to 50%. We study its impact on the number of frequent general patterns and the runtime of the algorithm. We notice that when the percentage is 80%, the number of frequent general patterns obtained is close and does not exceed the number of frequent traditional patterns, where when the percentage is lower, the number of frequent general patterns obtained exceeds the number of frequent traditional patterns. However, concerning the runtime of the algorithm, we notice that the minimum item similarity does not have a significant impact on the runtime of the GSPM algorithm. Therefore, we consider that the most adequate value of the minimum item similarity percentage for this specific data set is 80%. It allows us to obtain a significant but limited number of general patterns in a limited runtime. In conclusion to the experiments, we have noticed from the results that the minimum support promising parameter has a significant impact on the number of frequent general patterns, as well as on the number of the, on the runtime of the algorithm. This, in fact, confirms our definition of the promising patterns, which are patterns that are almost frequent, which means that their support value should not be much lower than the support value of the traditional frequent patterns, because if it is much lower than the frequent patterns, much lower than the support value of frequent patterns, then the algorithm would obtain a huge number of frequent general patterns with a long runtime of the algorithm. Concerning the minimum item similarity percentage, we notice that it has a significant impact on the number of obtained frequent general patterns, but it has no significant impact on the runtime. As our objective is to obtain a limited number of frequent general patterns in a limited runtime, then we consider high percentages of the minimum item similarity. However, if we consider that our objective is different, for example, our objective is to identify a huge number of frequent patterns as possible, we can set lower percentages of minimum item similarity, and we can obtain a huge number of frequent general with a limited runtime of the algorithm. We can also notice that GSPM is obviously more efficient than the data integration approach provided in the literature in terms of the huge number of patterns produced by the traditional approach and in terms of the redundancy among the patterns obtained, where GSPM algorithm does not allow redundancy among its obtained patterns, and in terms also of the runtime of the algorithm. Now we move to the conclusion of the thesis. We have proposed a new general sequential pattern mining algorithm called a GSPM algorithm, which allows obtaining traditional frequent general patterns. And in order to solve the problem of a limited number of traditional frequent patterns, it also obtains the frequent general patterns, which allow to recover the lost sequential activities. We noticed from the experiments that we have achieved the goals that we have set, which is to obtain an adequate number of frequent general patterns in a limited runtime of the algorithm. And if we look at GSPM from a multi-source point of view, we notice that it is more efficient than the approaches proposed in the literature mainly because it adopts a selective mining strategy of the multi-source data, where it starts with mining a main source, the first source, as our objective is the analyzing the sequential activities of students. It starts with the sequential data source, and then it only relies on a complementary source when it needs additional data to recover the lost sequential activities. This basically limits the complexity of the algorithm. And because we have this multi-source structure, we are able to obtain patterns that are in a hybrid form, which are patterns that contain various kinds of information. Our future work is mainly divided into three parts: the short-term, mid-term, and long-term future work. As a short-term future work, we aim at applying GSPM in the domain of education as long as we obtain our education in the METAL project, in order to prove the efficiency of the GSPM in the domain of education and in order to apply this domain in education, and also in order to prove that GSPM algorithm is a generic algorithm that can be applied on different domains and it is not restricted to only one domain. A second short-term future work is concerning the pattern and item similarity measures that we have set. Concerning the pattern similarity measure that we have introduced, it actually detects the similarity among the patterns which strictly have the same size, where in future work we aim at adopting more advanced similarity measures concerning the pattern similarity in order to be able to detect the similarity among patterns of different lengths. Concerning the item similarity measure, concerning the textual attributes in the item similarity measure, our proposed item similarity measure detects that two attributes are the same if they are exactly the same. However, we aim at considering a more advanced similarity measure, which allows to detect, for example, the semantics among different attributes. For example, if they have similarities between them, we can able to know that these attributes are similar, or we can consider them as common. As a midterm future work, we aim at managing the contextual and the complementary relations at the same time, and this can be done by integrating the contextual approach in the GSPM algorithm, which allows us to obtain frequent contextual general patterns, which are frequent patterns that are specific and general at the same time. A second midterm future work is providing recommendations of users' behavior in order to be able to concretely use our obtained frequent patterns in an applicative domain where we can provide recommendations of users' behavior. For example, we can provide recommendations to students where we can recommend educational resources to the students in order to help them improve their academic performance in class. This can be obtained by building association rules where we can use the antecedents of the rules in order to match the profiles of the students, and the consequence of the rules are thus used to provide the recommendations of educational resources. In our current GSPM algorithm, we obtain as an output a set of frequent general patterns where GSPM is capable of obtaining multiple generalizations in a pattern. However, we are not able to identify a certain hierarchical structure which allows us to identify multi-level generalizations. Therefore, as a long-term future work, adopting an approach or proposing a new approach that makes multi-level generalizations and allows us thus to obtain multi-level general patterns. Thank you.